Today we're going to learn probably the most important technique in all of optimization, called linear programming. To see why it matters so much, let's do some event planning. I found us a nice pub downtown. They say $500 an hour for the venue. They work with an event caterer. The caterer charges $20 per attendee for food. Let's gather together all of our costs. We also have some constraints. The event needs to admit at least 50 people, but not more than 150. And we also have a budget of $3,000. Our goal is to figure out how long the event can be while satisfying all the constraints. Believe it or not, this problem is hiding a triangle. Our costs and constraints can be viewed as geometry, and in this case, our problem becomes a triangle. This view of optimizing resources using geometry is called linear optimization or linear programming. It was used as a secret tool by the Allies in World War II. It helped drive the Soviet economy during the Cold War, and it led to a Nobel Prize for its creator. So let's check it out. Let's gather up all our info. To find the geometry in the problem, we need some axes to graph the constraints on. But we don't want an X and Y axes. We want one axis for attendees and one for the length of the event. Representing problems with abstract axes that represent the state of the problem is known as a state space. Every point in the state space corresponds to some combination of event length and number of attendees. Our event planning also has some constraints we should consider. Our first constraint is that the event limit will have to be somewhere between 50 and 150 attendees. In our state space graph, that means the point representing the optimal configuration for an event needs to lie somewhere between these two lines. At least 50, but no more than 150. That's the first constraint represented, so what about costs? Each person costs $20 in catering, and each hour costs $500 in venue fees. That leads to this equation for our total costs. We have a budget of $3,000, and if we spent all of that on the $20 person catering fees, we could afford 150 people. That corresponds to this point in our state space. If we didn't have any catering and spent all the $3,000 on the $500 an hour event fee, we could afford a 6-hour event. That corresponds to this new point in our state space here. Also, any balance of attendees and hours that lies on the line between these 2 points will also add up to exactly $3,000. For example, this point here shows a 3-hour event with 75 people, which adds up to $1,500 in event fees and $1,500 in catering for a total of $3,000. This leads to a new line constraint. Anything on this line is exactly $3,000. So our chosen configuration needs to be on or below this line. That takes care of all our constraints listed here, but there is an additional hidden constraint that we need to reserve the venue for 0 or more hours. So what area of our state space satisfies all of our constraints? Well, we can see it's this triangle here in the middle. As long as the event configuration lies within this triangle, the corresponding event will be in budget and be within our target attendee limits. This triangle is called the triangle of feasibility because every point in the triangle is a feasible solution. The left side of the triangle enforces a non-negative event length of at least 0 hours. The bottom side enforces that we can cater for at least 50 attendees, and the diagonal constrains the total cost to $3,000 or less. We still need to find what point exactly maximizes our goal, in this case maximizing the length of the event. We can see from the feasibility triangle that the possible event lengths range from 0 hours to 4 hours. So that vertex at 4 hours and 50 attendees maximizes the event length, given our other constraints and budgets. It is the mathematically optimal solution to this problem. That's linear programming. Mathematically speaking, linear programming is typically formalized like this. We have a state vector x, with each dimension representing some resources, and we need to find a value for the vector x that maximizes our goal or objective function. The equation of what we want to maximize is stored as a set of weights c that tells us the relative importance of maximizing each dimension within our state factor. The state x is then subject to a set of linear constraints that are represented by a scaling matrix A and a vector of limits b. And finally, we don't typically allow any resources optimized to be negative. You can't call and book a catering event for negative 10 people and then make the company give you $200 back. Surprisingly, the idea of linear programming dates back to the late 1930s, when Soviet mathematicians like Leonid Kanitrovich were working with the communist government to optimize the production of goods. His works, including the book, The Mathematical Method of Production Planning and Organization, led the CIA to call him an internationally recognized genius, and eventually resulted in Kanitrovich winning the Nobel Prize in economics. Thanks to the Cold War, the idea of linear programming was trapped in the Soviet Union, waiting for Kanatrovich's insight and optimizations to catch on. In America, the same idea was independently reinvented by George Dantzig and John von Neumann. Von Neumann's impact was discussed in a previous video, but Dantzig is also a superstar in his own right. The true story of him mistaking an important unsolved problem for his math homework and then solving it inspired part of the movie Good Will Hunting. Dantzig invented his approach to linear programming in the late 40s while working for the US Air Force to optimize military logistics for World War II. The method was initially kept secret by the government and did not become widespread until after the war. While neither Dantzig nor von Neumann won the Nobel Prize, the top prizes in mathematical optimization and in operations theory are literally the Dantzig Prize and von Neumann Prize, respectively. I want to show a more complex example of linear programming, but somehow the fields of centralized economic planning and wartime munitions management didn't seem like the right fit for a YouTube audience. So let's go cooking. Maybe you have a bake sale coming up, and you're going to bake some delicious cookies and snack bars. A batch of your famous oatmeal cookies takes 3 cups of sugar and 1 cup of oats. Your snack bars are a bit healthier, with one batch only taking 1 cup of sugar and 2 cups of oats. But you only have 10 cups of sugar and 10 cups of oats, which limits how many batches you can make. So what combination of cookies and bars gives you the most total batches? Like before, let's pull all the relevant information together and create an area to graph our constraints. Again, we should not think of these as x and y axes, but as axes to represent how many batches of cookies and snack bars we'll make. Our first constraint is to think about the oats. We only have 10 cups of oats, with a batch of cookies taking up 1 cup of oats and a batch of snack bars taking up 2. This means 2 times batches of snack bars plus 1 times batches of cookies must be less than or equal to 10, or else we'll run out of oats. What does this constraint look like in the state space? Well, if we cook only cookies, no snack bars, we'll have enough oats for 10 batches of cookies. That's this point here at 0, 10. And if we were to cook only snack bars, they use more oats, so we'd only have enough oats for 5 batches, which corresponds to this point at 5, 0. Connecting a line between these 2 points shows the span of all the different possible combinations that stay within 10 cup of oats. What about sugar? We also have a 10 cup limit, so we need a sugar constraint. A snack bar uses 1 cup of sugar and a cookie 3 cups. So we need 1 times batches of bars plus 3 times batches of cookies to be 10 or less. Making only cookies means we have enough sugar for 3 1/3 batches of cookies, while cooking only snack bars means we have enough sugar for 10 batches of bars. Again, connecting the line between these 2 points covers all possible other combinations of bars and cookies within this limit. In addition to the constraints from oats and sugar, we need to forbid cooking negative batches. This leads to this 4-sided shape for a feasibility polygon. The constraints on the left and bottom enforce no negative-sized batches. The next constraint ensures that most 10 cups of oats are used, and the last constraint that at most 10 cups of sugar are used. We still need to meet our goal. In this case, we need to maximize the total batches cooked. Whenever you have linear constraints and the goal of maximizing a weighted combination of the elements in your state vector, then the optimal solution will always lie on one of the vertices of the feasibility polygon. This means we just need to check which of the 4 corners has the most total batches. This point at 0, 0 has no batches. Here, we only have 3 1/3 batches of cookies. And here, we have 5 batches of snack bars. And here, we have 2 batches of cookies and 4 batches of snack bars, for 6 batches total. That's the biggest of the 4 vertices, so it's the optimal choice for this problem, and it's the most batches of baked goods we could possibly make with these ingredients. If you want to put this all into code, programming the key steps for linear programming is surprisingly direct. We can represent the line with the equation ax plus by plus c equals 0. And if we choose a different value for the constants a, b, and c, we get a different line. Linear programming also needs us to find the intersection point between these 2 lines. In Python, we can represent the line as a class that stores the 3 constants that define the line, a, b, and c. And the code for intersecting 2 lines is shown here and can be found via some basic algebra. The inequality constraint on nuts and sugar can be rewritten as an equality to find the constraint's boundary. These constraint lines can then be intersected with each other to find the vertices that might have the optimal configuration. And in this case, the first answer we check is the optimal. In general, we would need to check every possible intersection of the constraints. In practice, we probably want to scale up past 2 constraints and 2 resources. If we go back to the baked goods example, maybe we're running low on eggs and we only have enough for 3 batches of cookies. We can represent that as a new line constraint, which cuts through our feasibility region like this. And maybe we've promised to make at least 1 batch of snack bars. That leads to another new line constraint, which again cuts through the feasibility region like this. The resulting 5-sided shape has 5 potentially optimal vertices, and we can test each one against the objective we're trying to maximize. If you just want the largest total batch size, this is the optimal vertex. But maybe you're trying to maximize profits, and cookies will sell for a lot more than snack bars, so then this vertex would be optimal. If you don't want to write your own linear programming code, there are of course lots of excellent tools already out there. A great option is the GNU mathematical programming language, GMPL, which lets you encode optimization problems with pretty straightforward code. For example, here's the code for the baking problem, saying that we need a non-negative amount of cookies and bars, that we want to maximize our profit, and specifying constraints due to limited amounts of oats and sugar. Using the web-based solver link below, we can then quickly get the optimal solution and even visualize the constraint space. We can also use the code to easily scale up the problem. Maybe I also want to make brownies. We can add the expected profit for each brownie batch, account for the sugar brownies need, and even add another constraint on the brownies and cookies based on how much chocolate we have. With the code, it's also easy to do things like tweak costs. Maybe we want to have the amount of sugar we use in our snack bars. Rerunning the program quickly tells us that we'll make the most money with about 4 1/3 batches of snack bars, 1 1/3 batches of cookies, and just under 2 batches of brownies. To recap, we can represent the state space of an optimization problem visually, with each axis representing a resource we have. Linear constraints can then be used to represent limits on these weighted combination of resources. And finally, geometric optimization can be used to identify vertices in the feasible region and test each vertex to see which is optimal for our current objective. It turns out there are many other problems that can be solved with a very similar geometric approach, but we'll have to save that topic for when I see you in a future video.